All right, so today we're going to do a very brief arc tangent, inverse tangent lesson. And the only reason is because you've already been through arc sine. You've already been through inverse cosine. You know what's happening. You know that we're flipping the x and the y. You know that we're going to have to restrict it in some way. So it doesn't take the third time through. It should go a lot quicker. Okay, so we're going to do that. And then we're going to get into compositions of trig functions. And there's three different kinds of compositions that we have to get through in the next 2 days. There's unit circles, which we'll get through today. There's non-unit circles, which we'll start today. We'll do more of tomorrow. And then there's algebraics, okay? And then we'll get to tomorrow. We'll get to algebraics tomorrow, okay? All right, so let's talk arc tangent, inverse tangent, whichever one you want to call it. So, last week, Friday, you graphed the tangent function. It's in your notes. It waves. It's got vertical asymptotes on the over 2's. Okay, so pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on and so forth. That's where it's got vertical asymptotes. And then it's got the funky, like, I call it cubic graph, because that's really x cubed inside of there going on. Okay? Just as with sines and cosines, we're going to take any point that's on here. For instance, here is the point pi over 4, comma 1. Okay, we're going to take that point, and we're going to switch those x's and those y's. Okay, we've done that. We did that for sine. We did that for cosine. We're doing the same thing for tangent. So that then is going to become the point 1, comma pi over 4. And all of these then would happen. This one over here would be, what would that be? 5 pi over 4. Comma 1 would then be 1 comma 5 pi over 4. And so we would get these tangent waves, if you will. We would get them stacked on top of one another, and so we would stack them vertically. And that's not going to be a function, so we have to restrict it. So how we go about restricting it is we just take that middle one right around 0. Okay? So here is, oops, went too far. Here is inverse tangent or arc tangent of x. Let's talk a little bit about the domain of arc tangent. What would the domain be of the inverse tangent function? All real numbers, because it's going off forever and ever and ever. It's not restricted between 1 and negative 1 like sine and cosine was. So my domain here is all real numbers. What would the range be of it? Switched around, right? Because we go smaller ones first. Negative pi over 2 to pi over 2. Inclusive or exclusive? Why exclusive? They're asymptotes?
Yeah.
Okay. Yep. Because on actual tangent, pi over 2 and negative pi over 2 are undefined. So those are vertical asymptotes. So when we invert it, those vertical asymptotes become horizontal asymptotes, and we can't get there. So it's exclusive negative pi over 2 to pi over 2. So where on the unit circle am I looking? Left half? Well, where is negative pi over 2 to pi over 2 on the unit circle? We've seen it before. No? Just stretching. That's the right half. Same as sine. Okay. The only difference with sine is the pi over 2 and negative pi over 2 are included in sine. Here, they're excluded in sine. We can't have an answer come out with inverse tangent to be pi over 2 or negative pi over 2. Okay? Let's try some. So we've got inverse tangent of 1, or we could say that this is arctangent of 1. Same thing. In my brain, I'm still asking those same questions. Where on the right side of the unit circle is tangent equal to 1? Same question, just has a little more work involved with it now, because tangent is not just the x coordinate or just the y coordinate. Okay? Tangent is y divided by x, so I've got to do a little work. So if a fraction is equal to 1, y over x, what can you tell me about y and x? They're equal, they're the same. So for this particular one, I'm saying to myself, where on the right side of the unit circle is sine equal to cosine, x equal to y? Here? Here. Yep, right there. So it's going to be pi over 4. Asking myself, where right half of the unit circle is tangent equal to 0. So that's y over x. So if a fraction is equal to 0, what has to be true? Top is 0. So y has to be 0. So sine has to be 0. Sine 0? Sine 0. Sine 0. Sine 0. Yep. So that means this is 0. Okay? You now try those 4. So for me, I'm thinking, oops, it's already an arctangent. I don't need an arctangent, I need an inverse tangent. To me, I'm thinking of this as the inverse tangent of negative square root of 3 over 1. So I want my square root of 3 to be on the top. So that means that my sine needs to have the square root of 3 in it. And it's going to have to be, one of them is going to have to be negative. Here at pi over 3, the sine has the square root of 3, and that would be on top. Okay, but they're not both negative, so I've got to go down here to what should be 5 pi over 3, but it turns out being, because we're restricted to the right side, it is negative pi over 3.
But it's bigger than pi over 2, so it can't be 5
Pi over 3 is not bigger than pi over 2.
It can't be 5
Oh, yes.
3.
Correct. Yes. Yeah. It's just like sine. You want it to be 5 pi over 3 because that's where you're looking at, but we are restricting it to between negative pi over 2 and pi over 2, so that's why it's negative pi over 3. Yep. Just like sine. Good? Okay. Arctangent of negative 1, so that would be inverse tangent of negative 1. So that would be where they're the same, but one's positive, one's negative. I'm looking at 7 pi over 4, but we're going to write it as negative pi over 4. Inverse tangent of negative root 3 over 3. Oops. Oops. Come on. Really, by now you should realize that the square root of 3 over 3 is really 1 over the square root of 3. Okay? So I'm looking for now the square root of 3 needs to be on the bottom, so the cosine needs to have the square root of 3, one of them being negative. That puts me at negative pi over 6. And that one's going to be pi over 3 because it's the same logic we had for number 3, just not now both needed to be positive. Questions, comments, concerns, clarifications? It's the same thing. Same thing.
How come on these ones we can't do anything below the 0? Or we have to...
In quadrant 4?
Yeah.
Number 3 is in quadrant 4, number 4 is in quadrant 4, number 5 is in quadrant 4.
Yeah, I guess.
All those, because we're down here. It just, but you're not seeing the positive. You're seeing, like in number 3, you're seeing pi over 3.
Yeah.
But really we're down here, so it's negative pi over 3. Because that's this angle.
Yeah. Okay,
Right there.
that makes sense.
Yep. Good? All righty. You try those 3. Agree with those. Questions on any of those 3? Number 2, cosine, inverse cosine, we're looking top half from yesterday. So on the top half, I need to know where my cosine value is -1. Cosine is x. Top half, cosine value of -1 happens at pi. Good? All right. Let's go on to compositions of functions now. Now, with a composition of functions, you're going to have 2 trig functions. Okay? And it's going to be, you're going to have to evaluate one and then use that value to evaluate the second one. And we were debating in the last class. We couldn't come to a conclusion if it was Disney, Pixar, or DreamWorks. But it's your favorite animated movie. We're working inside out. Okay? So we start on the inside. It's not mine. I can tell you that right now. Okay? It's not, but I say it anyways. You do? Okay. It's been a while since I've seen it, to be fair. And I didn't see Inside Out 2 yet either. Yeah. Okay. So we're going to start on the inside, meaning I'm going to start here, and I'm going to say, all right, arc cosine of 1/2. Well, arc cosine, that's top half of the unit circle. Where on the top half of the unit circle is cosine equal to 1/2? Pi over 3. So that angle is pi over 3. With me on that? Then I have to take the sine of that. So now I go to pi over 3, and I take the sine of that, and I get root 3 over 2. And that is my answer. Okay. So I start on the inside, and I've got the inverse sine of negative root 3 over 2. What is the inverse sine of negative root 3 over 2? There you go. I knew what you meant, but it was like, okay, sooner or later she's going to figure out it's not negative 3 pi. Negative pi over 3. Okay. And then we need to take the cosine of that. So what is the cosine at negative pi over 3? 1/2. Questions, comments, concerns, clarifications? You try those two.
Oh yeah,
Yeah.
it was pi over 6.
Yeah.
Yeah.
Agree that that is pi over 6.
Yes.
Then we need to take the cosine of that. And the cosine at pi over 6 is root 3 over 2. Interesting. Interesting. Okay, let's see if that holds. Okay. Inverse sine at negative root 2 over 2. Pi over 4. So then we need to take the sine of pi over 4, which is root 2 over 2. Is that going to work all the time? It should, right? In theory, it should, because they're inverses, right? All right, let's try it. Let's see if it works all the time. Try those two. All right, so sine at pi over 3 is square root 3 over 2, right? Then I still have to take the inverse sine of that. Yes? Okay. Right side unit circle, where is sine square root 3 over 2? Pi over 3. So it's working out so far. Right? Okay. What is the sine at 5 pi over 3? Negative root 3 over 2? Now I got to take the inverse sine of that. Right side of the unit circle, where is sine negative root 3 over 2? Negative pi over 3. Ruh-roh. But if you gave me 5 pi over 3, it would be wrong. Yeah. 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 It's the same spot, but we have to label it differently because of those darn sign restrictions. Okay? Let's see about cosine, if it works for cosine. Cosine at 2 pi over 3 gets me negative 1/2. And then inverse cosine of negative 1/2 would be 2 pi over 3.
So 60%.
See why I said it now? Okay. Cosine at 5 pi over 3 is 1/2. Then I gotta take the arc cosine of that. And so then that would be pi over 3. What was that? It would be positive pi over 3. Because it's cosine and cosine's on the top half. Yeah. So that takes away the argument of it's in the same spot every time. Okay? Okay? Questions on any of those? Let's jump off the unit circle. Well, I shouldn't say jump off the unit circle, but let's go to non-circle problems. Okay? Just like with the unit circle, we had angles in standard position. I got a sneeze building, so if I pause every once in a while, I'm trying to not chew all over everything. Okay? Alright? So we're still going to have angles in standard position. So that means the vertex is at the origin. The initial ray is the positive x axis. Okay? And then we're going to adjust our triangles from there. Okay? You will not have a quadrant 3 triangle in this. Okay? Because sine and tangent both live in, or inverse sines and inverse tangents only live in quadrants 1 and 4. Inverse cosine only lives in quadrants 1 and 2. So this is the no-fly zone. Okay? So on algebraic and non-unit circle ones, and really even on unit circle ones, you'll never be in quadrant 3. Okay? All right? So, still starting on the inside, arc cosine is going to produce for us some angle theta. Okay? Well, where is that angle theta? Well, let's figure that out. cosine from our SOHCAHTOA was adjacent over hypotenuse. Ka. Okay? So that puts me as a positive cosine would be in quadrant number 1. So I'm going to draw myself a quadrant number 1 triangle. It's going to have an adjacent side of 4 and a hypotenuse of 5, which is then also going to produce our theta right there. So this is the sine of theta. Sine of theta is opposite over hypotenuse. So I need to find that missing side. If you didn't realize that this was a Pythagorean triple, then you would have to use the Pythagorean theorem. And figure out that that missing side is 3. So then the sine at theta would be 3/5. Know your Pythagorean triples. 3, 4, 5 is the most common. Also off of that, if I multiply them all by the same number, like 2, 6, 8, 10 is a Pythagorean triple. Okay. 9, 12, 15. Okay. That's the most common one. The next most common one is your 5, 12, 13. Third most common, 8, 15, 17. Okay. Inverse sine of 5/13 is going to produce my theta. So I need to basically just find the cosine of that theta. Cosine is positive in quadrant number 1. Excuse me, sine is positive in quadrant number 1. So we've got a 5 there, we've got a 13 there, which then gives us a 12 using our Pythagorean theorem for that one. And there is our theta. So the cosine here would be 12 over 13. Agree? You try those two. Cosine is negative in quadrant number 2. Cosine is adjacent over hypotenuse. Pythagorean theorem says that this then is going to be 15. So the tangent of theta then would be opposite, which would be 15, over adjacent, which would be negative 8. So I'm going to put negative 15 over 8 because I like my negatives on the top, not on the bottom. Yes, ma'am.
Is it making a triangle off of the horizontal getting like the theta prime thing, or is that not what they do?
That's it. Theta prime and theta would have the same values. Yep. Yep. We're not finding the actual angle, so we don't have to worry about theta prime right now. But the sines, the cosines, and the tangent are all similar in theta prime and theta. Yep. Okay. Sine is negative down here in quadrant 4. So that's going to be an opposite is negative 5. A hypotenuse is 13, which leaves me with, oops, wrong color. Didn't click in. Of 12 there. Secant is the reciprocal of cosine. So the cosine here for theta, the cosine of theta is going to be 12 over 13. Secant is the reciprocal of that. So this is going to be 13 over 12. Questions, comments, concerns, clarifications? I will hand out to you now the next sheet in your ongoing improvement or your ongoing building homework packet that will be due on Tuesday.